Hello. So let's do an analysis analytically of an IIR filter defined by a difference equation. And we are asked here to find the transfer function or the system function. 0.5 by n minus 1. We immediately recognize that this is an IIR filter because the output not only depends on the inputs of x of n, but also on previous outputs, you see x of n minus 1. And the fact that you have that recursion is what enables to reduce the number of coefficients required. You are using the fact that something was already previously computed, and you're using that previous output to reduce the overall computation of this filter. So again, this is an IIR filter, infinite impulse response filter, because we have a difference equation where the output not only depends on the inputs, present and previous inputs if it is causal, but also of previous outputs, if it is causal again. Again, let me just mention this. If y of n is a function only of x of n, any x of n for any n, we're going to say for any n and any k belonging to C, any function of them, this will be FIR. If, however, it is a function of both x of n and y of n, so of the input and previous and outputs, if it is causal, previous outputs, but if it is non-causal, it could be anything. Then we have infinite impulse response. Okay. And we will say that indeed these filters always have an infinite impulse response due to the recursion. Okay, so this is the difference equation. Let's find the transfer function or the system function. To find the system function, we take the C transform. Okay, C transform. And so we have that the C transform of y of n is capital Y of C. And we have 0.5, a delayed version. So this is C to the minus 1, Y of C, minus 3, X of C, plus 2, C to the minus 1, X of C. When we have used the property that if X of n is X of C, then X of n minus n0, or I'm going to say n minus k, transforms as C to the minus k X of C. This is the only C transform pair that we have used here. Now, we can group these terms, and so we have Y of C minus 0.5 C to the minus 1 Y of C equals, I just move this over here, or I subtracted on both sides of the equation the minus 0.5 C to the minus 1 Y of C. We are left with 3 X of C plus 2 C to the minus 1 X of C. We can factor, so we have 1 minus 0.5 C to the minus 1 Y of C. This is equal to, we are going to factor that too, and we have minus 3 plus 2 C to the minus 1 X of C. Now, Y or X, H of C, the system function, is equal to Y of C divided by X of C. And so over here, if we divide both sides by X of C, and then we solve here, we divide both sides by this same factor, both sides of the equation, we end up with minus 3 to c to the minus 1, 1 minus 0.5 c to the minus 1. And so this is our system function here. Now you recall the system function was a complete characterization of the system. Okay. From the system function, we could find, for instance, the output in the C domain of the system, h of c, multiplying the system function times the C transform of the input. You could do this. You could also go from the system function, and so from this then, we could also calculate the output, y of n, doing the inverse C transform. C transform. We could also go from the system function by also doing the inverse C transform to h of n, where this is the impulse response, right? And remember that from the impulse response we were able to assess causality, stability, the output for any other input, frequency response. It was a complete characterization of an LTI system. Well, it is also here. In fact, you can see that over here, if you evaluate h of c, the system function, for c equals e to the j omega hat, you end up with h of e to the j omega hat is equivalent to the discrete time Fourier transform, which, by the way, it is equal to the coefficients here, this y of e to the j omega hat, x e to the j omega hat, or, in this case, 3 to e to the j omega hat minus 1 divided by 1 minus 0.5 e to the minus j omega hat, which is like doing the, here is equivalent to doing the discrete time Fourier transform, or discrete time Fourier transform of the output over the input, or the discrete time Fourier transform of this numerator polynomial over the denominator polynomial. Now remember here, the roots of the numerator are called the zeros, and they null the frequency, they pull the frequency down, and the roots of the denominator are called the poles, and they make the frequency go to infinity. Now, the same way that we were able to do stability for any system, looking at the bounded input, bounded output, meaning if I have an input x of n, which is less than infinity, meaning it is a number, a particular number, then if the output is less than infinity, meaning it is a particular number, the system is stable. Now this was for any system without thinking about the structure of the system. Could be LTI, could not be LTI. If the system is LTI, we could have a more powerful test of stability that was based on you pick the absolute value of the impulse response, you add it from minus infinity to infinity. If it is less than infinity, if it is finite, the system is stable. And this is the proof that you could use for FIR filters. Being a finite impulse response, a finite number of filter coefficients are always finite. If LTI with a rational function, with a numerator polynomial, denominator polynomial, like in this case, you could also base it on the poles being contained in the unit circle. Meaning over here, we're going to be able to find the roots of the numerator, roots of the denominator, Then you have the real part, the binary part. You have here the C plane, and you have the unit circle. This is the frequency, and this is a omega hat. This being 0 or 2 pi, which is the sampling frequency. This is pi, or half the sampling frequency. And the location of the poles, being within the unit circle, is the way you're going to assess the stability of these IIR filters. So to recap, we have a difference equation where the output not only depends on inputs, but also on, notice, other outputs, previous outputs. Therefore, it is IIR. To analyze this IIR filter, the most powerful technique that we have is the C-transform. We take the C-transform of both sides of the equation. To do something like this, what you need is that the C-transform of a shifted, we get C to the minus K here, and this is, by the way, why in the block diagrams you see the delay operator presented as a C to the minus 1. Okay? So you take the Fourier transform, put all the factors in one side, the ones that depend on the output, the ones that depend on the input, and then basically you just solve it. And with that you have the system function. The system function being a complete characterization of the system. With it you can find the impulse response. With it you can find the output in the C domain. With it you can find the frequency response by evaluating the frequency around the unit circle. With it you can assess stability. Everything that there is to know about the system is contained in the system function. And this is equivalent to, in the continuous time, h of s, the transfer function that we evaluated for RLC circuits, for instance, using the Laplace transform. Thank you.